So good afternoon, everyone. The topic of my presentation is to understand and explore what can we do with batteries after they have ended their life in an electric vehicle. And the best way to explain is always with a figure. So here you can see, let's suppose that we have an initial stage here before we start in the manufacturing, right, where we manufacture new cells. Those new cells, we can use them to design a battery pack. So the presentations that were just coming before mine are just perfect, so that we can design this new battery pack and we can implement it in a vehicle where it will be used for traction purposes, and also it can be used for grid applications. The most simple one would be recharging the vehicle itself or participating in grid services, either through residential or commercial connection. So the battery in this first life can be living there for 10 years, a bit more, a bit less, depending on how we are using that vehicle. And once those cells have reached their end of life, which we define as when the battery has lost 20 to 30% of the initial capacity. That means that we have 70 to 80% remaining capacity in the battery that we could use. So the only options that we can have after we finish our use in an electric vehicle are two. The most direct one would be going directly into recycling stage, where we just disassemble the pack, extract the materials that could be used and repurposed either in battery sectors or others like cobalt, nickel, lithium, and maybe repurpose parts of the electronics wiring internally in the battery manufacturing, or just discard them. So that is the first option. The second option would be, if we have that 20 to 30% lost capacity, which means we have a 70 to 80 remaining capacity, why can't we extract the batteries from the vehicle? We're going to disassemble the battery pack. So with the aged cells, we'll have to grade them to understand how aged they are, which is the aging dispersion in the pack. And then we can reassemble a new pack that we can use in another application that normally will be milder than the first application in the electric vehicle. So this means that the battery can have a second life in a grid or residential, commercial type of application. And the length of life that can have in this application can be of 10 years, depending on the age of that battery. And after this second life, we could actually go to the final stage of recycling, where we can either extract the material, repurpose parts in electronics. So then if we do this second option, what we have is a longer, we're nearly doubling the life cycle of that battery, so it's going to be better for environmental concerns if we are postponing that recycling stage. And we are also offering lower cost batteries for this second life application. Now, in recent years, this second life applications has really been taking off. The expectations for second life is to have globally around 50 gigawatt hours of second life by 2030. Of course, that is a big projection out there, but we are seeing a very rapid growth. Now, the options that we are seeing in industry are very different. There are vehicle manufacturers that are choosing to go directly to recycling. They're not interested in taking care of this second business, as their main business is still their vehicle application. Other vehicle manufacturers are interested in this second life, not engaged directly, so they will allow for other companies to buy those batteries, and those companies will take care of their repurposing. Now, legally, there can be some responsibility from the vehicle manufacturer, so sometimes they are involved to a certain point to kind of check mark and say, okay, what you're doing with my batteries is still okay. We are confident with what you're doing. We approve that second life application, but they are not involved themselves. Other vehicle manufacturers are choosing to actually open a business option in their own companies where they are repurposing their own vehicle batteries in grid applications. Normally to do that, they are partnering with renewable energy companies, normally solar companies, so that they can provide the used battery pack from their own vehicles and partner with that solar company. The solar company puts the PV, they put the battery, and then they figure out the inverter. So those are a bit the trends that we are seeing right now. Now, I've grouped it into 3 big questions, although each of them has a much higher number of internal questions there. But these would be the 3 main questions that we can have when thinking about battery repurposing. The first one, what batteries can we repurpose of all the ones that we are seeing in the electric vehicle sector? How do we select and assemble the cells that we're going to use for that second life? And third one, for what applications can we use each of those batteries depending on their technology and aging? So we're going to see a bit the 3 questions, and we're going to kind of analyze some internal questions that we have in each case. So the first one, what batteries can be repurposed? Now, the current pool of electric vehicles, we have to wait until that vehicle has ended its life to be able to use it in that second life. So that means that we are dealing with technologies that were at the front line 10 or 15 years ago but are not in use currently. That means that we're going to see now that we're going to have nickel metal hydride are available. We're going to see several lithium-based technologies and their evolutions as the technology has changed and the vehicle manufacturers have adopted them. This makes things complicated, and the last speaker, if you were listening, it actually gives a good idea about it, because each of those batteries, if you're looking at physics-based models, we're going to have a high number of parameters for each of those batteries. Now, this means that if I'm dealing, even if it's lithium-based, if I'm looking at NCAs, NMCs, LFPs type of batteries, each of those is going to have different parameters, each of them 10 to 20. So this industry is facing the challenge of having to work with that type of battery and in age conditions, which makes it even more uncertain. The added complications are having different form factors. Form factors changes. Now 18650 is a standard that is changing. We have pouch type, prismatic type cells. We have different types of cooling system needs and different connectors. So even something as simple as a connector can pose a challenge when you are receiving 1,200 battery cells, and each of them requires a different connector. So this will vary by technology. What we've seen is that the technologies that are more available to be used are going to be LFP, also NMCs batteries, not NCAs as much because they have a shorter cycle life. The batteries that can be repurposed, and I'll kind of look a bit more into this point, is one of the main challenges is, well, it depends on how you use that battery during the first life, right? During the vehicle application life. However, we're going to have a huge number of variations of that vehicle application life, and it's going to depend on a large amount of parameters, and I'm going to give an example right now. So I'm going to skip a bit the testing until the next slide. So here's an example of first life variations that I can have in an electric vehicle. So I can have variations of temperature distribution, of external temperature distribution, by the way, not internal in the pack. And this is relevant for those batteries that are going to be passively cooled. So there's no liquid cooling, so the external temperature will affect, especially for those locations that are hotter during the summer. So this will mean that the capacity degradation that I'm going to see in those batteries is going to be larger. So even for the same vehicle coming from different locations, that is going to be a factor. What is also going to be a factor in that first life? We're going to see the effect of, for example, driving behavior. Are you normally an aggressive driver in your acceleration and braking, mild driver, or a gentle driver? And here we show the effect on the SOC variation for city driving and for highway driving. And these two are typical normalized driving cycles. What more variations can we have in a first life? We can have participation of vehicles to grid when that is possible, and we can either choose to engage or not in peak shaving, for example, with a solar panel. We could decide to help with peak shaving at a commercial location and work towards frequency regulation, or we can choose to have no utility services. So there are some variations in the total ampere hour through output that we put in our battery, depending on the services that we decide to engage. Now, the decision on engaging in those services may not be completely technical, but actually benefit-driven if we have incentives to do so. So what I'm trying to underline here is a bit what I was putting on this point, that we have a huge variation excuse me, of first life usage. So when the industry receives those battery cells, there is very limited information on what that cell has done in its first life. There is as limited as an information translation, but it could be things like mileage that vehicle has been driven. It can be a zip code where that vehicle drove, but it is very limited information to protect driver personal information. So this is a huge challenge as this industry has to assess the stage or the aging stage of that battery at that time, but with very little information of how it was being used. We'll come back later. Another challenge that we are facing when deciding which battery to repurpose is we have to make that decision of which battery can be repurposed. We know it has been aged, we don't know how it was aged, and we do know that the aging is going to depend on the material level aging. Now, we do not have access to that material level aging because it would require to open up the battery, take samples of the electrodes, and test them. So that means cell destruction. That battery is no longer useful. So it's not possible to evaluate it. And we know that the aging processes are complex and a variable depending on the technology we are dealing with. So we can have, for example, here we have a chart where we can see how temperature effects can either create lithium plating, which means the lithium, instead of being intercalated between the electrodes, it plates itself as a layer on an electrode, which means whatever lithium is plated is not usable anymore for intercalation. We can have a solid electrolyte interface where we have a growth of a layer around the electrode, which is going to make difficult for the lithium to intercalate. And we can have mechanics of materials problems in a structure with cracking or degradation, which is going to lower the quality of the electrolyte. So all of these elements are going to create a capacity loss and a power loss. So we know that these two final outputs of the process are going to come out of a model. They're going to be measurable at the system level, but whatever is happening internally, we're going to have very little information about it. So any type of concentration of lithium in the solid, concentration of lithium in the electrolyte, there is not much that we can know here, at least from a testing standpoint. So how do we decide what batteries can actually be repurposed? First thing, there's a physical inspection to see if the battery has been dented or cracked. And then we have to test it to quantify the remaining capacity that I could use in that second life. Now, that testing is normally electrically driven, and the two previous speakers went a bit over the modeling process, so I don't have to cover that. Most of them are going to be focused on the time domain, so being able to test the capacity of the battery, so doing a capacity test, doing simple resistance measurements to know the lumped equivalent resistance of that cell. Other tests, like the one that I showed to the right, is a frequency domain test, where we can extract a much more complex impedance spectra of my battery that goes from very low frequency and increases to very high frequency, so that we can know which is going to be the dynamic behavior of that battery, which is going to help us to assess the power fade of that battery cell. However, these tests are very time intensive and equipment is also very costly. So normally this industry will focus more on time domain tests to try to shorten the time and the equipment cost. Now for the equipment, it is challenging because the cells and the battery packs that come in to these warehouses come in different shapes, forms, voltages, and current ratings. So we're going to have cells that are in the lower range, in the 1.2 volts, and we're going to have others that are in the 3 to 4.2 volts, and in different capacities depending on the choice that the vehicle manufacturer did. So from a testing standpoint, you have a challenge in deciding what equipment do you buy to test, and how many cells can you test at a time. Again, if you're having big amounts of batteries coming in every day, having the equipment to test 500 batteries at a time can be very challenging. This means it is also very labor intensive, and both things of equipment and labor intensity makes scalability a bit of a concern. Actually, for the repurposing of batteries, labor cost can be up to 30% of the cost of repurposing a battery. So then how are the battery, if we move to the second question, how are the battery cells assembled? So once the batteries have been tested, we will establish what capacity is remaining in each of those cells, and we'll establish which is the resistance in each of those cells. So with that, we know capacity fade and power fade. Now, they are normally classified, right, and being grouped together so that the ones that are closer in capacity, they will form a category, for example, A. And then as they get worse, they get into category B, C, D, and there's a point at which there's no interest in using those batteries anymore, and they will go directly into recycling. So they are classified a bit statistically, but in a very simple way. The challenge with this is having a variable stock, right? Take in mind that these industries are in the middle in between receiving batteries from the electric vehicles, but providing packs for grid and commercial applications. So if they need a certain number of battery packs, they need to have enough coming in from the battery electric vehicle sector to be able to repurpose enough of them to create a pack for the grid application. So that can be a challenge to have enough of them. This means that the batteries are normally stored in warehouses where they're being kept until they can be repurposed for that application. So until the client requests that. This means that now we have a bit of a problem internally to track the self-discharge of that cell while it is sitting in the warehouse. Normally it is sitting without being monitored, so whenever you take that battery from the shelf to use it, now you may have to face that. You have to retest that battery or recharge it or spend some time and equipment on it to put it up to par. So absolutely the process can be further automated because the selection of the cells is still pretty manual because the volumes are still small enough, although they are ramping up so fast that the process needs a much higher automation, especially in the decision-making testing, so that we can move faster in the process and we can cut down on the cost of that battery repurposing. Now, for what applications are they more appropriate? Well, it's going to depend on what type of battery I have left, right? So we had different grades, imagine A, B, C, and D. Those applications that can be more power demanding than maybe only those cells that were graded as A are available for that application. Others that are less demanding, you can use the cells that were classified as C. However, that classification, again, is still done a bit manually. There's not a big automation behind that. The possibilities that we have is anything from commercial, for example, with peak shaving, if there is a PV, as backup instead of a generator, deferring transmission and distribution cost, for example, in substations for transformer, to change old transformers for new transformers, area regulations to match generation and load in a very fast time window, residential and community storage, especially when they are connected to PV, and other customer-specific ones. For example, they may want batteries that are available for charging other battery applications that are of a lower energy demand. So there are a lot of other customer-specific ones. However, the biggest challenge with this is there is a strong uncertainty that is propagated from the minute we're starting to use the electric vehicle on our batteries in our first life until the very last minute when we are using it in a second life. So that propagation of uncertainty starts the minute that we are all driving our vehicles, which could be exactly the same in different areas with different grid services, different charging patterns and driving behaviors. So that uncertainty propagates to come down to what capacity are we losing in each of our cases and what applications can we use it for as a second life. There is, let me finish something here first. There is also the challenge of once you generate your battery pack, once you have decided this is going to be my second life battery pack, I've decided what cells are close together in capacity that they can work as a full battery pack. Depending on what technologies we have, the self-discharge of those cells as aged cells, like not only aged but super aged in the sense that they've gone beyond the aging of what an electric vehicle application is looking at, can pose challenges in the balancing of that battery pack. So it adds to complicating our BMS's design to make sure that we have a safe second life battery and that is going to last for as long as the customer is expecting. What future trends I think that are necessary in the second life battery industry? Definitely more data-driven approaches. Because we have, as I said here in the last point, because we have a very strong uncertainty propagation in the use of the battery in the first life and in the second life, if we can take advantage of Internet of Things, where we have a lot of more elements, included batteries connected to the internet, connected to other systems, if we could have more information translated or handed from one life to the other, we could make better decisions about how we're going to use that battery in a second life. Either providing the data, and this is something that has to be explored. Do we store the data in the cloud for those that are driving the vehicles? Do they require very passive and low-cost sensing on the battery pack that is going to decide what data is relevant, and then that is given with the battery when it's handed off to the second life industry? It also calls to trying to understand what data is actually relevant. The problem with batteries is life is very long, but dynamics are also relevant. So what time window is relevant, and what data do you keep, what data do you throw away? So computer science approaches that either use machine learning, if we had Internet of Things, and if we could have the data of all those batteries, means that we could learn of how other batteries are aging to better predict how the batteries that are coming in, for example, if that industry is always receiving batteries from one side of the country, they will know from that location that, in general, you can statistically model which is going to be the capacity degradation that you normally have from that part of the country that is going to be related to temperature profiles, for example, traffic, etc., so that you can accelerate the processing of that battery in the second life if you are using the information from previous batteries that have been tested. Also, smarter stock shelf life tracking, where we can actually know what is happening to the battery while it is being stored, although the challenge here is keeping it low cost and actually saving time rather than adding time and cost. Optimizing the cell assembly so that we do it in a way that is not as manual, but that is actually can be automated. And once that the battery is actually out there as a second life, from an academic point of view, considering battery life, not only narrowing the focus to first life as electric vehicle or second life, but actually as a multi-life, where we can come up with strategies to control the batteries and evaluate the batteries as a whole system, including one life after the other. For that, for my taste, what is interesting is the fact that we have the batteries moving from one location to the other, like really, right? Because we take it from a vehicle and we may repurpose it in a completely different location for a completely different purpose, means that we have batteries migrating from one location to the other doing different things and aging as they are in each life. Interestingly enough, and that's things that we are exploring in my NSF Career Award, is can we learn from the computer science approaches used in natural systems? In natural systems, they are very used to working with systems that age, like animals, plants, etc. And they are used to the fact that they will migrate between locations and that they will age while they do that. And it's not by chance that in battery research, one of the most typical aging equations is actually based on the Arrhenius equation that comes from degradation processes in natural systems. So I think that there is a lot that we can learn from remote tracking, that it's being used for natural systems, in the tracking of populations, in the scalability of models between populations and individuals, and in understanding how the aging of a battery depends on the system or the ecosystem it's working in, and what specific circumstances that battery faces in each life, and how does it change, how can that affect its use as a second life. Okay, so with this, I finish.
Thank you, Lucia. Any questions? Please.
Thank you for the talk. A very comprehensive look at what's going to happen. So look into your crystal ball. What do you think, percentage-wise, batteries that are available now or in the near future will be, have a second life to them? 50%, 10%, 90%? Do you have a feeling?
At least a 50%, I would say. But again, it depends. One thing is what we can do from a technology point of view, and another is there a business model for it? And is that company, is it agreeing to do that business model? So ideally 100%. I think 50% would be reasonable, considering that there will be a number of those that will not be usable for that second life.
Okay, thank you.
Any more questions? Yes.
When you get batteries that are essentially dead, what is the typical capacity of those batteries, and what level do you set to reuse a battery if the capacity is, say, under 50% or something?
For the capacity, I would say that you need at least 50% remaining of that capacity to be able to repurpose it. Anything below a 30%, that you cannot do anything with it. So yeah, you need at least 50% remaining of that capacity to be able to repurpose it for a second life. Part of the reason is, no matter the level of degradation of that cell, the processing that has to be done industrially is going to be the same. So you're going to have to spend the same time on a battery that will provide you a bigger revenue than the one that will provide you a smaller revenue. So you will naturally choose those battery cells that will provide you a bigger revenue for the same amount of time and equipment use. So yeah, you need at least for my taste, at least a 50%.
Would you typically expect the batteries to be at zero state of charge when you receive them?
By the time they finish their second life? I don't expect them to be at 0% state of charge, because For example, in lithium technologies, once you go below 20%, the behavior of the battery starts to be funky. You do not want to get into that 20%. BMSs may not even allow it, so they will establish their boundaries. So I don't expect for that whole 50%, for example, if you put that number, to be used in a second life. Most probably, maybe a 70%, right, of that 50% will be used, and the rest will always remain unused. Now, could there be a third life? And you say, okay, I'm going to even, cross this lemon a bit further. I'm going to use it a bit more. That is going to be a cost decision. Maybe it's not worth it.
Thank you for your talk. Do you see, how early on in the process is this, like in the industry of things, and do you see there being public funding for this as well?
Public what?
Funding.
Okay.
Investments.
So we're not in the we're in the early stages, but not that early. So you'd be surprised. Companies I know of companies that have started this maybe 5 to 7 years ago. However, they've had very little input of batteries going in, as now we have a larger EV population that is actually ready to be decommissioned and repurposed. Now they're having a much larger influx of batteries. So we are maybe 10 to 20% into what the industry can take. So again, we are expecting huge growth to 2030 or 2040. On funding, I could not totally answer that, because I think that would be an industry. They tell you that if they have any benefit in terms of the land that they're using for the warehouse, there could be funding of that way, but I do not know, because I'm not working at the industry. Funding direct dollars to companies is always complicated, although they do have calls, right, as part of DOE or NSF, STTR and SBIR programs. But there is funding indirectly also through research collaborations with industries. So funding money doesn't have to be funneled directly. Sometimes it goes indirectly, with a lot of the times academia or universities providing the research that the companies need to push their programs further.
Any more questions? Okay, close this session. Thanks a lot, Lucia.